All right, so this is a key to worksheet on functions, worksheet number 9. And the direction says for each function, indicate the domain in interval notation. All right, and so if you look at number one is a linear function, and number 2 is a quadratic function. A linear function and a quadratic function are polynomial functions. And when you have a polynomial function, the domain is going to be all real numbers. So any real number in the domain, you're going to get a y value. All right, so in polynomial functions, the domain is always going to be all real numbers. And so in terms of the number line, so when you think of all real numbers on that number line, then everything is shaded. So every real number, that number line, any irrational number, any rational number, when you substitute a value for x, you're going to get a y value. And so in terms of interval notation, that's going to be negative infinity to infinity in both cases. So negative infinity to infinity. And whenever you have infinity, negative infinity, it's always going to be parentheses that's associated with it. Now, just a reminder, if you look at number 1, so remember number 1 is a linear function, right? And so we can graph a linear function by looking at the slope and y-intercept. So in this case, I have y, remember function notation, so g of x I can rewrite as y. So y equals 5x plus 2. So the slope is 5 and the y-intercept is a positive 2. So the graph's going to cross the y-axis at 2, so let's say that's here. And so to find another point in that line, remember this is a line, to find another point in the line, I'm going to use a slope. So slope, remember, rise over run. So I'm going to go up 5 and to the right 1. So 1, 2, 3, 4, 5, and then to the right 1. And so notice that your graph looks like this. Remember the arrows on both ends. So as you go from left to right, remember this is an arrow, so it keeps on going down. So you're going from negative infinity all the way to positive infinity. And then number two is a quadratic function. And the graph of a quadratic function is a parabola that either goes up or it goes down. But regardless, if you look at a coordinate plane, so if you let's say you have something that looks like this, a parabola, remember arrows on both sides, it could be pointing down like this one is, but no matter which one it is, remember, be careful how I drew this. It just keeps going like this. It doesn't go straight up, otherwise it would no longer be a function. But it kind of goes like this. All right, and so you're going from negative infinity to positive infinity. So that's the idea behind numbers 1 and 2. Now, number 3 through, I think the rest of them, yes, number 3 through number 8, all of those are rational functions. And remember, when you dealt with a fraction in the past, you could never divide by 0. So that's one of the things that you remember about 0. So for example, if you take your calculator and you say 4 divided by 0 and you press equal, you're going to get an error. So you cannot divide by 0. So what you want to do in these cases, in 3 through 8, is find out what value of x makes the denominator 0. So where are these x values going to be 0? You don't have to worry about the numerator. Don't look at the numerator. You just don't want the denominator to be 0. So if you look at number 3, I'll go ahead and do that here. If you look at number 3, my denominator is x plus 3. And so if I set that equal to 0 and solve for x, I'm going to get x to be negative 3. What that means, what I found here, is that if I substitute negative 3 in for x, notice in my denominator, negative 3 plus 3 is 0, and 7 divided by 0 is undefined. And so when finding the domain, you're looking at the restrictions of the value of x. So what restrictions am I going to impose on x? What makes the denominator 0? So number 3, what makes the denominator 0? So that means that if I look at this in terms of a number line, and put negative 3 here, what that means is that I cannot use negative 3. I can use every other number but negative 3. And so notice when I put negative 3 on that number line and I cross it out, I then have two intervals that I can choose values of x for, and I will be able to substitute in here. The only number I cannot substitute is negative 3, because negative 3 makes that denominator 0, and 7 divided by 0 is undefined. And so therefore, when you put your domain in interval notation, you're going to go from left to right, and so I'm going from, remember these are arrows, I'm going from negative infinity all the way to negative 3. So this is how it's going to look, negative infinity, negative 3, parentheses, and parentheses because I cannot use negative 3. So you see I have a little x there. I cannot use negative 3. Negative 3 makes my denominator 0. So I'm going from negative infinity all the way to negative 3, and also that other interval, which is from negative 3 to positive infinity. So you're going to say union negative 3 to positive infinity. And so that's your domain. So when I graph this function, this rational function, I'm going to use every real number for x except negative 3. And what you're going to see when you graph these is that x equal negative 3, when you do graph it, that's going to be a vertical asymptote. So it will look something like this, just to kind of give you an idea. So here's x equal negative 3. This is x equal negative 3. And so your graph will look something like this. It'll look something like this. So in this case, you're going to have really then, remember what I just said though, that your domain is every real number except negative 3. So this negative 3 here is going to incorporate a vertical asymptote. There's a horizontal asymptote in here as well, but that's not what this is about. This worksheet's about. This worksheet's about finding the domain. And on this side, it's going to look like this. Let me go ahead and draw this part. So it's going to look like this. All right, so that's the graph. So you have this horizontal asymptote, which is the x-axis, and you have the vertical asymptote, which is x equal negative 3. You didn't have to know any of this to do this worksheet, but I'm just kind of giving you an idea of what this negative 3 means in terms of a graph. All right, so this graph here is a rough sketch of this function g of x and number 3. All right, but the way that you should do this to find the domain is find out what makes the denominator 0, put on the number line, cross it out, and then the intervals that's produced by that restriction is going to be your domain. So for example, if you look at number 4, so if I look at the denominator, all you have to do is look at the denominator, 3x minus 5, set that equal to 0, and solve for x. So when I solve for x, this is a linear equation, so I get 3x equal 5, so x equal 5/3. So that means that I cannot use 5/3, because if I put 5/3 in for x, 3 times 5, it doesn't matter what the numerator is. I'm just looking at the denominator. So 3 times 5/3 is 5, and 5 minus 5 is 0. So whatever this number is, divided by 0 is undefined. So that's your restriction. That means that the only number you cannot use for x is going to be 5/3. So put 5/3 in the number line, cross it out, and you have these two intervals. So all these other real numbers are going to be part of your domain. So when you go from left to right, you're going from negative infinity to 5/3, negative infinity to 5/3, parentheses because 5/3 is not in the domain, union, and then 5/3 to infinity. All right. Then when you look at number 5, I'm going to put number 5 here. So when you look at number 5, remember all you do is just look at the denominator. So my denominator is x, you set it equal to 0, and x is already by itself, right? So the domain will be every real number except 0. And so when you look at every other number and you shade it in like this, you have two intervals. So your domain is going to be from negative infinity to 0, union 0 to infinity. And that information is going to be useful when you graph these functions, because x equals 0 is going to be a vertical asymptote, just like you saw here, that vertical asymptote. That's denoted as a dotted vertical line. Number 6, we have this expression, and notice it's in factored form. So leave it in factored form, because if you look at this, you have two factors whose product is 0, right? And so remember, when you have two or more factors whose product is 0, then one of these factors has to be 0. That's that 0 factor property. So I'm going to set each one of these equal to 0. And in this case, I'm going to get two restrictions. This is 3 and negative 4. I cannot use either of those, because if I use 3, notice what happens. 3 minus 3 is 0, and it doesn't matter what this is, because 3 plus 4 is 7, right? But it didn't matter because this was 0. So 0 times any number is 0, and 5 divided by 0 is undefined. Same thing here, negative 4. If I put negative 4 into this factor, negative 4 plus 4 is 0. Whatever this is, well, negative 4 and a negative 3 is negative 7. Negative 7 times 0 is 0, and 5 divided by 0 is undefined. So you have two restrictions here. So you're going to put both of those on the number line. Make sure you put them in order. So negative 4 is to the left of 3. Cross them out like I'm doing, and notice that these two restrictions divide the number line into 3 intervals this time. So instead of 2 intervals, this one's going to have 3. And so you go from left to right, so negative infinity to negative 4, union, and then 4 to, that should be negative 4. Negative 4, union negative 4 to 3, and then union 3 to infinity. All right, number 7, we have x squared minus 25 equals 0. Now notice this is a quadratic equation. Now this is a quadratic equation as well, because if you FOIL it out, you'll get x squared plus x minus 12. But it was in factored form. Here, you want to solve this quadratic equation, but it's not in factored form. But one of the things you learned, several things you could do with this, you know that this is the difference of two squares, so I can factor this as the difference of two squares, couldn't I? And so now this looks like this. And so I could set each of those factors equal to 0, so I get x minus 5 equals 0, x plus 5 equals 0, and then solving these linear equations, I get x to be 5 and x to be negative 5. Now another way that some students probably did this was they looked at this equation and noticed that the x term is missing. All you have is an x squared and a constant. That x term is missing, so that means that you could easily get x squared by itself. So when I get x squared by itself, I get this, and then I could use the square root property. Remember though, when you use the square root property, that you have that plus or minus. And so the square root and the square undo each other, so you get x equal plus or minus. The square root of 25 is 5, and notice this and this are the same solutions. So it did not matter which approach you took. Now, once you get your restrictions, you're going to put that on the number line, so negative 5 and 5, and you're going to cross those out because you cannot use those. So my domain will be every real number except those two real numbers, negative 5 and 5. And so notice again, you have these 3 intervals. And so when you put these intervals here, you're going to say negative infinity to negative 5, union negative 5 to 5, union 5 to infinity. All right, and then number 8, so you look at number 8, your denominator, remember all you do when looking at these rational functions is determine what makes my denominator 0. So when I take that denominator and I set that equal to 0, I get this quadratic equation. And I can solve this quadratic equation by factoring. This is factorable. Or I could use quadratic formula. You all know about the quadratic formula. But this is factorable, so I'm going to just go ahead and factor because it's quicker. So let's see, this is going to be 2x and x right here. And this is a positive 6, so there are several possibilities for positive 6. 6 and 1, negative 6, negative 1, 3, 2, negative 3, 2. And the one that works, though, is going to be 6 and 1. And 6 is going to have to go here, and 1 is going to have to go here. Now, always check in the end, just like you've done before. Notice that the middle term has a negative sign. So that means that these two have to be the same sign because they both have to be negative. Because remember, a negative times a negative is a positive. So that's the only way you can get a positive is for these signs in here to be the same, and they both have to be this middle sign here. And then let's just check, just remind you how to check this. So to check this, I'll just go ahead and do that here. So to check this, you're going to do first, outer, inner, last. So 2x times x is 2x squared. Now here's the outer. So the outer is a negative 12x. See that? Negative 12x. The inner is a negative 1x. And when you add them up, you get a negative 13x, which is what this is. And then the last, a negative 1 times a negative 6 is a positive 6. All right, so the way we factor this is correct. Now I'm going to use the zero factor property. So I'm going to set each of those equal to 0. So 2x minus 1 equals 0, x minus 6 equals 0, and then I'm going to solve each of those linear equations. So 2x equals 1, so x is 1/2. So there's one of my restrictions. Over here, x equals 6. So on the number line, I have 1/2, and I have 6. I cross those out because I cannot use those, right? And so the domain is going to be every real number except those. So every real number except those. So notice the 3 intervals here. So when I indicate the domain, you're going from negative infinity to 1/2, union, and then remember all parentheses here because those are restrictions, union 1/2 to 6, and then union 6 to infinity. So I'm going to go ahead and put union 6 to infinity. And that is it. So that's how you find the domain of polynomials and then rational functions. All right, so that is the key to this worksheet.